factorizing by completing the square. So we're very clear. Everything I do on this page, up to this little reminder, is the background information to the strategy of completing the square. Then after this, on the next page, will teach you the method for completing the square. So all these little things that I'm doing here are giving us the background information that we need. They're not the actual concept that I want, or the procedure that I want you to do. So this is a perfect square. If I factorized it, that's x plus 3, x plus 3, so that's x plus 3 all squared. That's why it's a perfect square. It's an expression multiplied by itself. Now I can draw a perfect square as a square made up of squares and rectangles. And it's as if I'm doing the area of the square, this side times this side, and getting this result. So having x here gives me x squared. I need to get 6x and 9. And so if I've got a 3 here and here, x and 3, then 3 times x would give me 3x. 3 times x gives me 3x, and 3 times 3 gives me 9. So you can draw any binomial expansion as a rectangle, like this, and any perfect square can be drawn as a square with the expression on either side, and this shows us our factorized form. Now we can use this to find missing numbers in perfect squares. So if I told you that both of these expressions were perfect squares, well, we could draw a square and I'd know that I'd have to have x on each to get x squared. Then I need these two to add up to 8x, which says, and they're going to be the same, so that's got to be 4 to give me 4x, that's got to be 4 to give me 4x, and that means this is 4 times 4, which is 16. So if I did the same over, and if we wanted, that could mean that my question mark is 16, and it would be x plus 4 squared, factorized. So if I drew this little square here, then I know that this has to be an x at the start of each expression to give me x squared. 12x has to come from these two. I shouldn't have made rectangles there, but whatever. Which is going to have to be 6 and 6. So x times 6 is 6x, 6 times x is 6x, and so this missing number here, 6 times 6 is 36. So I've found the missing number in a perfect square. And incidentally, I've worked out what the factorizing would be, which is x plus 6 squared. X plus 6 times x plus 6. Now that's all very well if it's a perfect square and there's a missing number. And there'll be questions in the textbook where they say, you know, for just that, complete the perfect square. And you'd say, well, if it was a perfect square, you'd have a number here. What would that number be? Obviously, you don't actually need to draw a square. How did I get this number and this number? Well, I took the number in front of x, which you'll remember is b, x squared plus bx. And I know that's got to have to be split into 2. So I divided it by 2. And then I squared it to get the missing number in that perfect square. So b over 2 squared completes a perfect square. Totally separately to that, that was perfect squares. Just a reminder about difference of perfect squares and factorizing, because we're going to be using this concept as well. If I asked you to factorize this using a surds, you'd recognize that this is a difference of perfect squares. This is a perfect square, difference, and this can be written as a square if I write it as the square root of 20 squared. So this is x minus 2 squared minus the square root of 20 squared. And now I can see that this is a difference of perfect squares. And to factorize a difference of perfect squares, I start with, in brackets, the square root of the first term, x minus 2, minus the square root of the second term. And in the next brackets, I've got the square root of the first term, x minus 2, plus the square root of the second term. I have factorized this difference of perfect squares using surds. If these were not in normal numbers in surd form, you could combine those, but this is easiest to leave it like that. So a reminder about difference of perfect squares, factorizing using surds, and an introduction to completing a square and using b over 2 squared to complete a perfect square. Now, we use this to factorize expressions that we can't factorize just by inspecting because we don't see a nice easy factor. Normally when I factorize something, so if this was a nice helpful instead, x squared plus 4x minus 4, make it plus 4, I don't know. You'd look for factors of c that add to give b, and you'd go, hey look, it's 2, x plus 2, x plus 2, I've factorized it. But there's no factors of negative 7 that add to give me 4. And you'd probably sit there and look at it for a while and go, okay, well 7 and 1 is negative 7, no, none of it works. If this was a really nice useful number, that'd be fine, but it's not. What we're going to do is separate out this part and this part, and we're going to aim to make a difference of perfect squares, like this one, using the ability to complete a square. I'm going to complete this square and then have this tacked on the end. But obviously I can't just go changing stuff because I'll change the value of my expression. So let's just have a look at what I'd get if I did b over 2 squared for just this part here and completed the square. b is 4, so that's 4 over 2 squared. 4 divided by 2 is 2, 2 squared is 4. So if I completed this as a perfect square, I'd do x squared plus 4x plus 4, and as we saw before, because I just did it, that's really easy to factorize. It's a perfect square. But I can't just add 4 in there. The only way I can add 4 in there is also to take away 4. So, you've got to break this apart. You've got to have this little bit here, the ax squared plus bx, and I'm going to complete that as a perfect square. So, like this, x squared plus 4x. I know I've got to put plus 4 to complete that square. And I've put that in that bracket here. So I had this little bit there, and I said, I'm just going to complete that as a square. But the only way you can do this plus 4 is if you also take away 4. And I've also got my minus 7, which was hanging out here all the time. So as you can see, by putting in plus 4 minus 4, I haven't actually changed anything about the value of this expression. But I've made it so that I can factorize this bit here, which is kind of useful. So I have added and subtracted b over 2 all squared from this expression but be very, very careful to put it in after your bx. I'm separating this into two little parts. Now, factorize this perfect square, and I know it's going to be a perfect square because I completed the square to make a perfect square. It will always be the number inside this bracket. So if we just skip back here, you notice when I did b over 2 squared for this one, b was 8, b divided by 2 is 4, and that was the number that ended up here. 12 divided by 2 is 6, and that's the number that ended up in here. So I know where my b over 2 was 2. I'm going to get this is x plus 2, x plus 2. That's that. I've factorized that and it's a perfect square. This is always going to be a perfect square because I'm completing a perfect square. Over here, I've got minus 4 minus 7, and that's minus 11. This is a perfect square, x plus 2 squared. And now I've got a difference of perfect squares because I can use the strategy that we just learnt, or we just revised here, by making that negative 20 the square root of 20 squared. I'm going to write this as minus the square root of 11 squared, and that's a difference of perfect squares. This is first term, or first bracket, x plus 2 and root 11, and we'll make this one our plus. Second bracket, x plus 2, so that's the first one, and my root 11, and this one has to be minus. You've factorized something that you didn't think you could factorize by using this strategy called completing the square. So my steps are add and subtract b over 2 squared, and then factorize as dops. So this one here, there's no factors of negative 3 that give me negative 8, add to give me negative 8. So you find b over 2 and square it. b is negative 8, divide that by 2, this will be negative 4, and square it. Negative 4 squared is 16. Sorry, I just ran off the page there. Now remember that this number here is going to come in handy later on. This is the one that we're going to be adding and subtracting into here. Remember, I'm separating this out. This bit here is becoming a perfect square that I'm going to complete. Sorry about the lighting. This bit here is going to be the other end of a difference of perfect squares, because in here I'm going to add and subtract this number. Now obviously you don't have to go drawing all over it like this. I'm trying to illustrate what we're doing. So this equals x squared minus 8x plus 16 minus 16 goes in there, and don't forget that minus 3 that was hanging out with us. Remember then that this is going to be factorized on its own as a perfect square, and I'm just going to add or subtract what's happening over there. This lighting goes every time I put my hands in the way, I'm sorry. Factorize this, and you don't even need to think about it because the number in the brackets is this one over here. This is x minus 4 squared. And this is minus 16 minus another 3, which is negative 19, or minus 19. Once you've got it to there, as long as it's a difference of perfect squares, perfect square minus and a number, then I can write this as a surd squared. You could check if you can simplify your surd, but we can't in this case. And now it's a difference of perfect squares. X minus 4 is the square root of the first term. It goes at the start of the brackets. Root 19 is the square root of the second term. And it's plus and minus. You have factorized by completing the square. This one is an example of where it's not possible. So if we carefully find b over 2 squared, b is 2, so I've got 2 over 2 squared, which is 1. So I'm going to do plus 1 minus 1. X squared plus 2x plus 1 minus 1 plus 8. So I've put those in there. Factorize this bit. Now I know it's going to be 1. X plus 1 squared. Now this ends up as plus 7, and this is a plus. You can't use this method, because the only reason this method works is because we're using a difference of perfect squares to then factorize. I can't factorize this, so this cannot be factorized. And you'd say that. And incidentally, later on we'll learn about being unable to factorize things. And sometimes there'll be fractions involved. Now if your head is full at the moment, you might want to go and do some of the work that I've set and then come back to this after you think you've got your head around it, because I know this has been a long video. But if you want to keep going, or if you've come back to it, we find b over 2 squared. b is 3, this will be 3 over 2 squared. Now square this, leaving it in fraction form. 3 squared is 9, 2 squared is 4. Remember, this is going to be a number that's very useful, as well as this one. We want to complete the square, so in here we're going to add and subtract this number. Put our brackets around our first 3 terms, because I'm factorizing that. And this is not hard to factorize, because you know it's a perfect square, and you know that the number in the perfect square is what we got here in the brackets. Then we do have to do some fancy stuff with this. 9 over 4 plus a half. You'd change this to 2. Oh, it's minus 9 over 4 plus a half. Change this to 2 over 4. So I've got minus 7 over 4. And to factorize, it's a difference of perfect squares. I'm going to have to write this as, hang on a sec, I'll just write this one in, minus 7 over 4 square root of squared. Sorry, I got a bit messy there. And then we might need some more space. Sorry about that. In my brackets, I've got x plus 3 over 2 and minus. Now, square root of 7 and the square root of 4 can be done separately, because the square root of 4 is 2. So if we get kind of clever here, I've got minus the square root of 7 on 2. Next bracket, this term. And this was minus, so this is plus root 7 on 2. And the reason I manipulated that is because now this can actually be simplified, because I've got a common denominator here. So, x plus 3 minus root 7 on 2, x plus 3 plus root 7 on 2. So you can see we can get some rather complicated factorising happening by the end there.